Today we discuss again of transmission lines in the frequency domain, and our discussion includes the case in which there are losses in the transmission line. Losses are to different contributions. There are contributions due to finite conductivity conductors and also to lossy dielectrics, materials that are not ideal. So let's see how the equivalent circuit of a short section of transmission line of length dz is modified to account for the presence of losses in the line. These are the equations that correspond to the circuit in which losses are not present, which we describe the Z derivative of voltage and currents in terms of, as you see, imaginary contribution, because it relates, let's see, the current to the variation of voltage by an imaginary impedance, which is J omega L. And similarly, the variation of I respect to Z is related to the voltage by an imaginary admittance J omega C. So how do we modify this circuit to account for losses? We introduce losses, a term that accounts for losses, which is a resistance here, resistance per unit length, and a conductance here, conductance per unit length. These two aim to describe losses due to conductors R and to dielectrics G. Similarly, as L is the inductance per unit length, as we were discussing, R is the resistance per unit length and G is the conductance per unit length. So that the circuit is modified as you see here. There is a series resistance R dz and the shunt conductance G dz. So how do we compute R? It accounts for losses due to conductors, and as you see, we know that current distribution is limited to a short, very thin region around the conductor surface, which is in contact with the fields, and it is this yellow region, so that we can say that the current distribution is confined to this very thin, narrow yellow region around the conductor surface. The thickness of this region is the well-known skin depth, delta, that we have already computed for the case of plane waves. The expression for the skin depth is shown here. It depends on frequency, it depends on permeability, and it depends, of course, of conductivity of the metals. So the higher the conductivity of the metal, the thinner, as you see, is delta, the skin depth. Of course, the current distribution doesn't have to be constant here, but we assume that it is constant to simplify the computation. So we have that the resistance, total resistance of this short section of transmission line of length dz, R dot, is the resistance per unit length times dz itself. And the total resistance of this conductor for uniform current distribution can be computed as 1 over sigma, which is the resistivity, then times the length, which is dz, divided by the cross-section that is crossed by the current. This cross-section can be written approximately as the perimeter of the conductor times the skin depth delta. There is also a factor 2 that accounts for the fact that there are two conductors and therefore the double of power dissipation inside due to finite conductivity. In the general case, the two conductors can be of different diameter and therefore different perimeters, so that the total resistance is the sum of two terms. Each term is contributed by a single conductor, by the perimeter of a single conductor, as shown by this equation. For instance, for the coaxial cable, in which there are two conductors of different diameters, one is radius A, so diameter 2A, and the external one is diameter 2B, we can write the resistance per unit length by this term. Of course, resistance per unit length is obtained by dividing this expression for the total resistance by dz. Rs is a term that is known as surface resistivity. It's actually can be written as a square root of omega mu over 2 sigma, and it also can be written as 1 over sigma times delta. So as you see, the resistance per unit length of the coaxial is the surface resistivity that multiplies 1 over the perimeter of the internal conductor plus 1 over the perimeter of the external conductor. G, for concerns G, we observe that losses in dielectrics are represented by a complex dielectric constant, and therefore epsilon r, the relative dielectric constant, is multiplied by a term which is 1 minus j, the loss tangent of the electric type. This term, since the capacity per unit length capacitance per unit length is proportional to epsilon r, we observe that the capacitance per unit length becomes proportional to a complex term, because we introduced a complex dependency to epsilon r. If we multiply times j omega the result of the capacitance times this complex coefficient, we obtain a complex admittance. This complex admittance takes the form of admittance per unit length of G plus j omega c. This is therefore our conductance per unit length. If we carry out the computation for this case, we obtain an expression for G that depends on the capacitance per unit length by this formula omega c times the loss tangent. For instance, for the coaxial cable, since we know an expression for C, which is shown here, we obtain a value for the conductance simply by multiplying this expression times omega and times the loss tangent. So, what for concerns propagation, the presence of a complex coefficient that relates the variation of V respect to Z to I and the variation of I respect to Z to V introducing a complex dependency of this parameter that relates the wave equation for voltage and current. So that the solution to this equation is now a couple of waves in which the complex wave function is governed by a parameter gamma that is complex. The expression for gamma is the square root of gamma square, and therefore takes this expression. And the effect of this complex dependency is that gamma can be written as a real part, that is the attenuation along the line, plus an imaginary part that is the propagation. So that as a result of the presence of losses, we have attenuation in the direction of propagation. Similarly, since we have an expression for the voltage, we also have an expression for the current, and the relationship between the two for the single wave is called complex wave impedance, is actually complex, and it takes the form of r plus j omega L divided by G plus j omega C. A common units for attenuation is Neper per meter, the natural units, and for propagation is radian per meter. But since, as you see, Neper and radians are dimensionless quantities, we can actually add the two. So we can say that we can compare alpha expressed in Neper per meter to beta expressed in radians per meter, because actually the unit of these two is the same and is 1 over meters. And an alternative for alpha is also the dB, decibels per meter, which is related to the Neper per meter by this simple expression. So, a very important case is the special case of lines with low losses, in which the materials are close to ideal, so we have a very good conductors and we have good dielectrics. This condition corresponds to alpha being much less than beta. As we already said, we can compare alpha and beta because they actually, in practice, they have the same units. And this also corresponds to R being much less than omega L and G being much less than omega C. These two must hold for this to happen. In these cases, we can write for the characteristic impedance, which means for a single wave, the ratio between voltage and current, the real quantity, square root of L over C. So we can neglect the imaginary component in this. In the expression of characteristic impedance without making a great error in most practical cases. Not only that, we also have that the propagation constant is approximately the same as that in the lossless case. The propagation constant in the lossless case is omega square root of LC, so we take the same value. We only add an attenuation that can be written as the sum of the attenuation due to dielectrics plus the attenuation due to conductors. These two are obtained as function of Zc and of G and R. The two expressions are shown here. So, we have that voltage and currents attenuate with attenuation constant alpha. Power attenuates with an attenuation constant twice alpha, so that the power traveling along the line is the power at z equals 0 times the exponential minus 2 alpha z.